basic ingredients in a supervised learning algorithm is a data set containing a part of matching input and output. The inputs of supervised algorithm can take many shapes and form. Company fundamentals, transaction records, time series, news and report. They can either be raw data or transformation of raw audio into engineered features. The collection of features is often referred to as the design matrix and are the explanatory variable in our model. The output can also take many shapes and form. Buy-sell recommendation, credit scores, sentiment, parameters of the distribution, trajectories. The outputs are raw target values that the model will try to predict. We can also call them response variables or dependent variables. Now, using values of input-output pair, the goal of supervised learning is to learn what function can take examples that live in the input space and map them to the output space. It does so by learning over the whole data set what patterns of features for a given example are associated with its respective target. For example, we have as input commodity prices, past returns, supply and demand indicators, and as output, we have prices in 2 years, for example. The model we want to learn will be able to best predict the future output price given the input. So more formally, we learn a function f such that the inputs of x can be mapped to its output y. In other words, we want to learn the function of f that depends on x and the parameter set that will best predict y. Because it might not be possible to predict exactly the corresponding target value for every example in the set, we seek to learn the model that will reduce the overall prediction error. In supervised learning, there are two types of problems: regression and classification. Regression problems seek to learn to predict a continuous value. The function that we will learn can take on the following form. One of the simplest is the linear regression, where we try to fit a straight line going through a cloud of points. If we have a more complex relationship between x and y, we could model it with a polynomial regression. This way, we have more capacity to learn a model that is closer to the true function. Another commonly used algorithm is a decision tree. Decision trees partition the input space with conditions and assigns value to items in the partition. The second type of supervised learning problem is classification. Classification aims at finding the frontier that will separate two or more classes from each other. The logistic regression is one of the most commonly used algorithms for binary classification. We apply a sigmoidal function to linear transformation of x, because the sigmoidal will be bounded between 0 and 1. So we can interpret the output value as the likelihood of belonging to a given class. Another way to separate classes is with the support vector machine. Support vector machine do so by finding the highest margin between 2 points. In the case where the frontier between class is nonlinear, then we can use multilinear perceptron that we will explore in further details when we will describe feed-forward networks. Now, consider the following classification problem where we try to separate two classes. Because they're linearly separable, it is quite easy to use any model, whether we regress x on y linearly or with a logistic regression. We will get that the frontier is a linear combination of x1 and x2. The linear regression will output a real value between -infinity and infinity. For prediction, we can use an arbitrary threshold of, say, 0 to separate the classes. In the case of the logistic regression, the output will be between 0 and 1, and we can use the arbitrary threshold of 50% to separate the classes. In any case, both models will yield sensibly the same results. Now consider a more different classification problem, where the underlying distribution is the exclusive OR function. These classes are not linearly separable, so it's impossible to draw a straight frontier between them to separate the two classes. We can use a neural network because a neural network is a universal function approximator. Depending on the structure of the network, we will get different frontier that will separate the space differently. For this problem, a network of 2 layers with 2 nodes per layer is the closest approximation of our target distribution. Let us introduce you to the mechanics of feed-forward networks. We will focus on multi-class classification problem. We start with a data set of paired inputs and outputs denoted by X and Y respectively. The inputs are a collection of examples in D dimension. So if it's a black and white 128 by 128 image, that's 16,384 dimension vector. At the other end, we have our target values. Since we're doing M-class classification, the shape of Y is a one-hot encoded M-dimensional vector with zeros everywhere except for a 1 in the proper class. If we were doing regression, then our last target value would be a real number. So first, we start by feeding one example to the algorithm. We also need to initialize the parameter set, and for that we can use random values. The size of the parameter matrix W is a hyperparameter selected by the designer of the algorithm and should be determined with the help of a validation set. Usually, its dimension will be smaller than X to restrict information flow. After initialization, we can compute the values of the features of our first hidden layer. First, by applying the linear transformation to X by pre-multiplying the matrix W1 by X and adding B1 element-wise. Then, by applying the nonlinear activation function denoted by a sigma. The result is a vector of DH dimension because of the linear transformation in X. The result of this layer is called a hidden feature vector. The activation function we've used has a sigmoidal shape, but activation function may also take many different forms. Some are monotone, continuous, differentiable, or bounded, but they need not be restricted to those conditions. For example, the ReLU, for rectified linear unit, is a non-differentiable piecewise linear function that is unbounded. After computing the hidden feature layer, we can use our model output that will be used to make different prediction. First, we use the hidden feature computed in the previous layer. We apply a linear transformation by pre-multiplying with our second parameter matrix W2 and add the second constant B2 element-wise. Note that because we want this layer to output the likelihood of belonging to a specific class, the dimension of W needs to be those of the previous layer DH and the number of class M. Finally, we apply the softmax function, and the result is a vector of M dimensions with values bounded between 0 and 1. So by taking the argmax of this vector, we are choosing the class with the highest likelihood. The fitted or predicted values denoted by Y hat is a one-hot encoded vector with a 1 at the place of the predicted class. With this, we can now easily compare our prediction to the ground truth target label. The second step after the forward pass is to compute the loss function. The forward pass enabled us to compute predicted values by our model, and we also have their corresponding target values. By comparing those vectors, we can compute a measure of how successful the model is at classifying the data set. We call this performance measure a loss function, and it's denoted by L. If we average this function over the whole data set, then we will get a measure of how well we classified the whole data set. We call this empirical risk minimization. After computing the loss function, we can now proceed to the third step of our algorithm, which consists of backpropagating errors throughout our network to see how we can improve our predictions. To do so, we need to compute the gradient of the loss function with respect to every parameter by applying the chain rule throughout the various layers of the computational graph, given by the Jacobian matrix of the network. After backpropagating the errors throughout the network, we can go on to the next step, which consists of updating the values of every parameter in our model. We can update the parameter values by gradient descent. Gradient descent is an algorithm used to find an optimum in a surface Because the partial derivative of a function with respect to a variable will give the direction of the local optimum, and because we're doing empirical risk minimization, by taking a step in the opposite direction of the gradient, we will get closer to a minimum. The size of the step can be increased or decreased to reach the different areas on the lost surface. The fifth and final step is the most important one. We repeat the whole procedure, and with each iteration, the model will get better and better at classifying the dataset. Once the gains from one iteration to the other cease to produce marginally significant improvements, then we will say that the model converged to a solution. Please note, before using your model to make new predictions and make it more robust, make sure to have trained, validated, and tested your model on out-of-sample data. So in summary, in order to train your network, you must first feed inputs and compute prediction of y with the value of your initial parameter set. Then, you compute the overall loss of your model. Once that is done, you backpropagate errors by computing the gradients of the loss function with respect to every parameter. Then, use those gradients to update the values of the parameter, and repeat those steps until convergence. In this capsule, we saw how we can use a feed-forward network to learn how to predict the labels of a data set by updating our parameters with backpropagation. In the next capsule, we will learn how to use unsupervised learning to learn about the data itself.